Okay, welcome back, everyone. Hope you negotiated the break in the lectures, midterm assessments, whatever you had last week. Okay, as you can see, we're back with a new backdrop. We're moving on to the galaxies part of the course. But before we do that, then I'll just finish up what I left you with last time when we were looking at spectroscopic binary stars and determining masses, etc. So I left you with this radial velocity curve of two stars, A and B, to have a look at. And I was asking you to look at the sort of center of mass of the velocity of the center of mass of the binary system. Okay, just to think about what's going on in these curves, really, and how to actually measure the radial velocity amplitudes of both stars. So the thing to sort of look at here is to identify, this kind of blue line here, if you like, which is, you can see it's where it's the axes of symmetry, if you like, for the radial velocity curves, for both radial velocity curves. It's where they cross over. Okay, and so that line there runs through a radial velocity of plus 40 kilometers per second. Okay, so that is what you would identify as the velocity of the center of mass of the system, okay, down here. Okay, and that's because obviously both stars are orbiting around a center of mass, but that whole system can be moving through space relative to the sun. Okay, so that's what that velocity of center of mass means. It's the motion of the center of mass of that binary system relative to the sun. So when you're looking at measuring the amplitude of the motion, of the binary motion, you need to do that relative to the center of mass, not relative to the sun. So here, if you were measuring the radial velocity amplitude of star B, then you'd measure it from this line going up, so that's about 70 kilometers per second. And if you were doing it for star A, then you'd be looking over here, or you can do it over here, doesn't really matter, as about 25 kilometers per second. Okay, so that's how to sort of read these graphs, if you like, the radial velocity curves. If you've got a double line spectroscopic binary, if you've got a single line one, then obviously, again, you need to probably do half the peak to peak would be the easiest way to do it, because you wouldn't have this reference point. If you were, I didn't ask you to do this, but if you're interested about going on to use this information to then actually measure the masses of these two stars, then you can obviously read off the period quite easily here. Just look at one cycle and read off the period. So that's about 17.5 days. And so here I'm just setting out the calculation of masses. Now, of course, we've got the inclination in here, which we don't know. So one way to make progress is to just assume that this system is close to edge on, so that I is 90, and that you're seeing the full component of the radial velocity. And then you can just put all these numbers in. You've got the radial velocity amplitudes in kilometers per second that we just measured. You've got the period of 17 days that you can convert to seconds. Just put all the numbers in to this version of Kepler's third law, and you're going to get the total mass. And and obviously the mass ratio, as I discussed last time, is just the ratio of these two amplitudes. So you can see that here. Just make sure you get them the right way around. Okay. Star A, which is the more massive one, will have the smaller amplitude. Okay, so you can solve for both masses there. Okay, so that was the end of that topic. And now let us move on to galaxies. Okay, so in this first lecture, we're just going to set out what a galaxy is, the different types, and how to classify galaxies. So nothing very, mostly descriptive here to start with. So what is a galaxy? Well, basically, it's a gravitationally bound collection of stars and gas and dust, as we shall see. We're going to go on to talk about these components in subsequent lectures. But basically, it's a collection of stars. Okay, and you know, it'll be sort of isolated in space. It's, as we shall see, we live in our own galaxy called the Milky Way, but every other galaxy is outside of our galaxy, as it were. So nearly all the stars and examples of objects that I've been talking about up until now have been within our own galaxy, but now we're moving up in scale. We're moving outside our own galaxy to look at other galaxies out there in the universe. Okay. So like I say, most galaxies are, you know, well separated from each other. But as we shall see again in a subsequent lecture, some of them do have near neighbors, including our own, and they can interact together. So that's another subtopic that will come up. And if you're sort of looking at, you know, the universe as a whole, then you can think of the galaxies that dot about all around the universe as being the sort of the main visible component in terms of, you know, if you're looking at optical light or any bit of the electromagnetic radiation spectrum, then galaxies are the, you know, the main visible component of the universe. So let's start with some pictures. Galaxies do look very pretty. And we will come back to this object time and time again as an example, because it's basically the nearest sort of galaxy proper outside of the sort of Milky Way system, if you like. This is the so-called Andromeda galaxy, but also known as M31. So you will see this designation quite a few times. The M, just again, just a piece of information, just stands for the Messier catalogue, so a French astronomer who catalogue a lot of these sort of nebulous objects. You know, I've already shown you pictures of other nebulous objects like planetary nebulae and supernova, and these were all, and star clusters, and these were all lumped together by Messier. But as was found, you know, many years after he catalogued these objects, that these galaxies are a very different type of object to the sort of nebulae that we see in our own galaxy. So these are whole separate galaxies entirely. Okay, and you can see what you're really seeing here is just mostly just, you know, it's the starlight from a collection of stars here. I don't think I made the point just now, but galaxies like our own Milky Way, and we'll prove this to yourself later in the module, contain about 100 billion stars, something like that order. They can vary a lot, obviously. But the M31 here, the Andromeda galaxy, is very similar to our own galaxy. So if we were over there looking back at ourselves, we would see something very, very similar. So this is a good example to take. The other points of light that you can see on here, of course, are stars in our own galaxy that are sort of in the way, if you like. We're looking out through the stars in our galaxy. Of course, you can't really look in any direction in our own galaxy without you know, seeing foreground stars from our own galaxy. So that's what these other points of light are. Okay. But all of this collection of light here is due to this other galaxy. In fact, you can see two more galaxies here, which are actually near neighbors of this one. Okay, so let's now look at the different types of galaxies out there in the universe, and they basically just split up into three major types. So spirals, ellipticals, and irregulars. So hopefully you could already see there that M31 had a sort of spiral structure to it, and those are the ones we're going to look at first. So a spiral galaxy, again, a beautiful optical picture here of a spiral galaxy where, as we shall see, the spiral galaxy is actually a thin disk of in its sort of geometry, and it's rotating structure, and it's dominated by these so-called spiral arms, which obviously are the things that give it its name. So you can see here in this one, sort of two main spiral arms spiraling out from the center of the galaxy here. So they sort of unwind in that way. If you look at this picture for a minute, you might be able to sort of think to yourself, okay, well, which way round is this galaxy rotating, clockwise or anti-clockwise? I think just from looking at it and the way the arms are spiraling back this way, it looks like the galaxy is, you know, you had to guess, it was rotating sort of this way, so rotating clockwise, and you'd be correct. But we'll come on to it's not as simple as it first seems, actually. So we'll come back to the sort of spiral arms again in a subsequent lecture. Okay, but this is it's a thin disk, really. It's like a plate, and so this galaxy we happen to be seeing in a sort of face-on orientation, if you know what I mean. So we see it, and it's rotating around like this. Okay. I'll show you an example of an edge-on one in a moment. But firstly, let's start to apply some of the physics that we learned about stars in the first part of the module. So this is a sort of, as best as we can, a sort of true color picture. And you can see that there are, different parts of the galaxy are different colors. And we can now apply the knowledge about sort of different colors of different populations of stars that we learned in the first part to these galaxies. So you see the spiral arms here are full of what looks like relatively blue stars. Okay, so you can see them here as well. Okay, and so if you've got blue stars, then chances are that these are the sort of hot, young, massive main sequence stars, the sort of types of stars that we met in the open clusters, if you remember back to that lecture. In fact, you can see clusters of stars here, which basically are open clusters, if you like. Okay, you can see clusters of blue objects here. So that's exactly what you're seeing. But basically all the population along these spiral arms is dominated by those young, massive main sequence stars. And to use the terminology that we introduced recently, then these would be referred to as population 1 stars. Okay. Again, we're going to come on to this a bit more, but you can see these dark lanes here in the spiral arms. Okay, here, see them here as well. So these are actually what are called dust lanes. So these are clouds of sort of gas and dusty material that also inhabit the spiral arms. And so this is another feature of this. And it's actually this kind of material in these dense, dark, cold clouds here, as we shall see later, that are basically the locations where new stars can be born, okay, out of clouds of gas and dust. And so that's another feature of population 1 regions. The fact that they're young means that they were recently formed, and in fact, stars are continually being formed in these regions. And so population 1 is inevitably usually the young population 1 are associated with areas where new stars are continually forming. Okay, so that was a face-on view. Here's a more of an edge-on view. So if you tilt these spiral galaxies around and look at them edge-on, this is more the kind of thing that you see. So you can see there's quite a thin disk of material here. This one's not perfectly edge-on. You can see this, again, the dark dusty material now is very prominent, forming the sort of what we would call the plane or the disk of the spiral galaxy. But now a new feature comes into view here, much more clearly, which we will refer to as the bulge. Okay, and so this is more of a sort of a three-dimensional structure. Okay, they're usually a sort of an elliptical sort of bulge of stars in the center of the spiral galaxy. And again, you can see them here. And the thing to notice here is that the color is different. Okay, so here this is more of a red concentration of stars, much redder than the blue stars that you see in the spiral arm. So again, thinking back to what we learned about different sort of populations of stars and different types of clusters, if you're dominated by red light, that usually means that you've got an old population of stars, because all the young hot blue stars have evolved away off the main sequence and died, leaving behind just the lower mass main sequence stars and the red giants that form from them. So the light in these bulge populations here in the center of the galaxy is dominated by these old red giant stars. So that's the bulge there in the center. So that's more of an elliptical structure, centered around the very center of the galaxy, whereas the disk, which contains the spiral arms, rotates again about the center of the galaxy, but is much more of a planar structure and not a three-dimensional structure. So this bulge is basically full of old stars. So these are the population 2 stars. They can also have some of the older sort of population 1 type metal-rich objects as well. So having more heavy elements in them, as well as the metal-poor population 2 stars that have been around for a very long time. Okay. So the population here is analogous to the globular cluster type population, but this is not a globular cluster. This is a much bigger thing that's stuck in the middle of a spiral galaxy. Okay, now spiral galaxies themselves come in 2 different forms. Okay, you can have normal spirals, or you can have spirals like this. I admit this is a bit of an extreme example, just to make the point. These are referred to as barred galaxies, so they have a bar all the way up through here. So this is a long sort of linear structure that appears to be here. You can see that, and then you can see that 2 arms kind of swing off the end of this linear sort of structure here. So you've still got the bulge, okay, but then this bar is an elongated sort of structure that also is full of those kind of older red stars as well. Okay, so that's what we mean by a barred spiral galaxy. And these are quite common. About 40% of all spirals have this kind of bar structure in them as well. Okay. Okay, so let's move on to another major class of galaxies, and these are the elliptical galaxies. So you've got a picture of one here. It's this quite different looking object now. So these are much less structure in them. They're just sort of, usually elliptical in shape, hence the name. But they just have a smooth distribution of light that sort of gets brighter and brighter as you go into the center. So there's the concentration of stars gets more and more as you go into the center of the galaxy. And so these are all they're always just made up of these red population of stars. These galaxies are often called red and dead because there's not much else going on in them. So they're basically, again, full of these population 2 and old population 1 stars. So just an aging population. And you can see that there's no spiral arms, there's no dust, no gas structures in here, just that smooth variation intensity. And that means that there's no star formation going on because there's no gas and dust to form any new stars out of, which is again why they're aging. And these are 3-dimensional structures, so they're not flattened out by rotation like the spiral galaxies. So the angular momentum is what makes those spiral galaxies very flat, like rotating pancakes. Here, in elliptical galaxies, there's it's not that the whole galaxy, all the stars are all rotating around one axis. That's not happening. All the stars will be orbiting around the center of mass at the center of the galaxy, but they'll all be doing so in the random directions. Okay. And there's a big range of sizes of elliptical galaxies. The spiral galaxies have a bit of a range, but not such a wide range. Elliptical galaxies can be enormous, like this one. This is a very prominent example, fairly nearby, of a giant elliptical galaxy. But on the next slide, I'll show you a dwarf elliptical galaxy. Okay, so here you can see a sort of diddy one. This one's got about 1 million stars in it, whereas the previous one might have had about 10 to the 13 stars in it. They're real monsters. So this is, this collection of stars is only sort of 10 times bigger than the globular clusters that we talked about before, and not quite so concentrated as a globular cluster, as you can see in this picture. So again, this one's quite nearby. And again, it's just dominated by these old stars, no sign of any gas or dust here. Okay, and the last category is one called irregular galaxies. So as the name suggests, these basically don't really have any regular structure. And you might think, well, okay, well, it's a sort of a rag bag of things that we can't classify any other ways, but they are quite important in the whole history of the universe. There are a lot of these. They're usually fairly small, similar to the smaller spirals, or, well, usually smaller than a spiral galaxy, similar to the dwarf ellipticals in size. So, tens of millions of stars in them, that kind of thing. And they're also they're a mixture. Okay, so in this picture here, you can see some aspects that make them look a bit like features of spiral galaxies. So you've got dust lanes here and here, and some of these sort of nebulae where new stars are forming. So they do have plenty of gas and dust in them, and some young stars. Okay, but I think there's a general sort of glow around the back here. Well, not around the back, but in the background. But it's all mixed in. Sort of a reddish sort of background of starlight there, which is a collection of old stars, so the population 2. So you've got both in these irregular galaxies. So you've got a mix of young stars, like here, and a mixture of the old stars here as well. And no regular structure. As I said, fairly small. And here's another picture of a different one. Okay, so again, you've got this general red glow here, so a concentration of stars. So that's the sort of older population in red light that you can see there. But then you've got clusters of young blue stars here, and sort of nebulae associated with them that we're going to come on to discuss. So you've got a whole load of population 1 stars here, mixed in with a general bunch of older stars as well. So they're a real mixed bag. Okay, so that's an introduction to the different types of galaxy. Again, let's try and keep something quantitative and keep applying your knowledge. So I just want you to sort of have a go at working out the typical angular separation, so in arc seconds, of stars that are, again, a typical separation apart. So we saw in our galaxy that the typical distance to the next nearest star is about 1 parsec. But even the nearest galaxies, like sort of M31 that I showed you already, is nearly 1 megaparsec away, so 10 to the 6 parsecs away. So if 2 stars are 1 parsec apart physically, but at a distance of 1 megaparsec away from us, what is their angular separation is the question. Okay, so have a look at that, and we'll see what that means when we come back after the break.